Good afternoon, ISMA World. It gives me great pleasure to invite delegates from Brazil, Canada, China, the Czech Republic, Finland, France, Germany, Ghana, India, Italy, Japan, Mongolia, Portugal, South Africa. Special note here, welcome Hans-Peter Neth, the chairman of DMG's South African agent, Retagon. Switzerland, Turkey, United Arab Emirates, the UK, and the USA. And of course, our global partners are fully represented with delegates from AHP Merkel, Makino, Clarita, the GF Group, Messe Stuttgart, Moldeno, and the NIMS organization from the USA. Today is marks the first of a very exciting series of webinars where we're actually doing something different that ISMA has never done before. Now, let me start off by explaining a little bit about the Global Partner Program. The Global Partner Program is specifically designed to invite companies to join our ranks who can add value to our worldwide organization through innovation-driven technological development. It's specifically not designed as a marketing tool, but the consequences of joining us and doing a good job probably ends up doing just that. So, as I said, we have now allocated on our agenda an opportunity for each of our global partners to present to the world what they can do for our industry. So it's with a lot of pleasure that I invite representatives from the DMG group here today to present DMG MORI to the world. And we have here, and I'm now going to pass you over to Michael Kerbach, head of DMG MORI Aerospace Die and Mold Excellence Center, and Marcus Baumer, the sales director for DMG MORI Ultrasonic Laser Tech. Over to you, DMG MORI.
Yeah, thank you very much, Bob, for the nice introduction. And yeah, we welcome all of you warmly to our factory here in the south of Germany, Deckelmauer-Pfronten, one of the factories of DMG MORI. I'm here together with my colleague Marcus Bäumler, as just introduced, and we are happy to have you here. And we want to go into technology excellence in die and mold. We want to give you some ideas. Of course, we said it's not a marketing. We try to keep machines beside us, but we will talk about technologies, we will talk about solutions, and you will see in our agenda how we do this. Marcus, from you, some words?
Yeah, also from my side, a very warm welcome. Thank you for giving us the opportunity for this presentation. I'm quite excited to bring some news to you in regards to additive manufacturing. And at first, I think we start with Michael's presentation. Thank you.
Thank you, Marcus. So yeah, today we have collected our agenda where we, of course, give you some introduction about DMG MORI, who we are, what we are doing in die and mold industry, in which segments we are, and we show some solutions. We then go to the trends which are today available or which are in this industry, but what we see in this industry. We will go into digitalization, which is one of the 5 trends. I show you something on the machine tool, how we use digitalization on the machine tool in the process. Then we go at the end to additive manufacturing, which will be presented by Marcus later. And then we have time for question answers and hopefully interesting discussions with all the participants.
On that point, if I could just interject quickly.
Yes, please.
If any of the delegates present have questions, please enter them on the chat, and our secretariat, Manuel Oliveira, will actually be presenting them at the end of the session.
Good. Okay. Thank you. So we start with a short introduction, what we are, who we are. We see ourselves as a holistic approach in this industry. First, before we go into these details, I show you some information about DMG MORI. We have a global footprint of more than 100,000 customers worldwide. We have many sales service companies worldwide where we sell our machines, where we service our machines from. We have 15 production plants currently, with more than 12,000 employees, 100,000 customers worldwide, and in all the industries which need machining finally. From the factory point of view, said 15 factories. We have the DMG MORI Aktiengesellschaft, which is a headquarter in Bielefeld in the north of Germany. We are here in the south, in Fronten. We have also the DMG MORI Company Limited, with headquarter in Tokyo, in Japan, with factories in Japan, in China, as well as in the United States, in California. We have a wide range of machine tools. We don't talk about this in detail, just to give you an idea that we have many, many products in this business. To make it a little bit easier to give you an idea in which areas we are and which kind of technologies we are, we have turning technology, which are lathes. We have milling technology, so milling machines, machine centers, but we also mix them. We have turning machines which can do milling and grinding. We have milling machines which can do turning and grinding. So we have technology integration depending on workpieces. We find here always the right solution for each application. We have advanced technologies like ultrasonic supported machining. And we are used to work with lasers since a long time. We have laser tech as one of our segments. And in the die mold industry, you find this for shaping of molds, for example, to get your shape or your feature on the finished part later. And we can combine a milling machine and we put it in a laser and we can machine a mold, and then we use the laser to shape the surface here. Then we have additive manufacturing, a very growing segment here in DMG MORI. Markus will later talk about this. Automation is very important for us. We see this all later in the trends. Automation becomes more and more important. In the past, it was mass production. Today, even for single piece production, automation makes sense in a certain way. Digitalization is very important for DMG MORI. We have many solutions here. Today, we talk a little bit about this. Technology excellence means we have excellence centers for different industries like aerospace, die and mold, medical, semiconductor, and others, where we have specialists who take care of the specific needs of these industries, because the machine tool is doing milling or turning, but it depends what you are machining on the machine tool, and we can make sure that our customers get the dedicated solutions for their industries, for their needs. Of course, we also have training. We have academies here where we can train our customers. We have service to take care of the machine tools during the life cycle of these products. This gives you a little overview what DMG MORI is doing, and specifically in the die mold industry, in our die mold excellence center, we segment our let's say business in 4 areas. We have some daily business where we work with our application engineers who have a lot of experience in this industry to do some technical consulting. Sometimes we make studies based on customer applications. We propose, of course, a solution for the machine tool and for the automation if required. And we are also able to deliver turnkey solutions where we are responsible for the whole process and deliver the machine as a holistic approach, including the solution on the machine. We also look, of course, the future business, what will happen in the future in this industry, to be aware of this, to be prepared for this. We have a lot of partnerships with universities, institutes, associations like the ISMA and also the national associations, where we also are in close contact to understand what are the needs of our customers today, and of course in the future, that we get prepared for this. And of course, all our work is also based on a big partnership with many industrial companies, where we have solutions along the whole process chain, from programming, CAD/CAM systems to tools, clamping systems, and so on. So we are partnering here with many companies in this field to always be able to offer the best solution to our customers. The benefits, of course, for our customers is that they get a perfect solution finally, and we get also good feedback from this idea of technology excellence to be specified on these industries, pays back over the time for us and makes us really happy that this works, and customers really give us good feedback here. In which segments, of course, for which segments our machines can be used, we have, of course, a wide range of industries in this business. We have plastic injection molding, as you know. We have blow thermo molding. We have the metal world here with castings, with forming, hot forming. I don't go through the details which kind of solutions we have. When customers come to us, we look to the workpiece, to the size, which accuracies are required, how the surfaces should be, what is the geometry, how complex the parts are, what is the budget of the customer, and then we make sure that we can offer the right solution for our customers. when we go a little bit in the details of some case studies, how this can look like, and when you are all experts from this industry, here in this example, we see injection molding, mold assembly, and this is here for headlamp for automotive industry, and we understand that this is a quite complex tool assembly. There are different type of mechanical parts which need to be machined, and as you have seen before with our portfolio, we can make sure that we find a proper solution for every kind of component here. Of course, when we look to our technology, which we have specifically in this factory here, Deckelmarb-Fronten, where we are on the 5-axis machining, we are interested in the, for example, the cavity inserts here, and I brought a nice example here of the cavity insert of this headlamp mold, because we did a case study on this for us to learn and to show our customers how capable our machines are. This component, you can imagine the size of this piece. We invested a lot of energy together with our partners, invested some engineering here. At the end, we produced more than 450 NC files and 1.6 gigabyte of data to make this 5-axis machining happen. You can find this movie on YouTube by just searching for advanced machining strategies and die and mold. But I show you the movie to bring some emotion into this, or I feel some emotion when I see this. So we can see now in this movie some cutting strategies which we involved in this, put into this movie. Of course, this only shows some finished machining operations. You can imagine there's much more in this 1.6 gigabyte of NC data to make the part, but it shows how capable today 5-axis machining is to make these kind of parts in a very productive and efficient way. Here in this example here, we have worked together with Paul Horn for tools, for example. We have worked with Hypermill for the programming, and only in a partnership this can happen. We cannot do this alone. We have the machine tool. We have, of course, people who can do this, but we need the experts also from the other companies who are involved in this. The other, we need the other specialists to make something like this happen and to demonstrate this to our customers so that they can understand how efficient and how productive parts like this can be done. So we can watch from outside forever to these movies. We really like them. This movie is on YouTube since 1 week, and we have, I think, today 20,000 clicks and very nice comments on this. Yeah, there are other examples. Here's an aluminum rim for hot forming die. Good example here. Of course, many of our other customers from other industries underestimate the effort which has to be put into a part like this. And finally, it's more than 120 hours of machining. You have seen on my title, I'm more coming from the aerospace industry. We have also parts like this in the aerospace industry, but also on this industry, long times of machining is sometimes very useful, very much used. We see here some examples for the processes. This is very detailed, of course. We show this to customers to make them confident that we understand how to make these parts. And of course, we know what is the requirement for the machine tool, that the machine tool is able to make such forms here, such molds. Because here's at the moment the finish, the roughing process with 2 different tools. We have also here the finishing here, and also the last tool here. You have to imagine runs almost 70 hours on this rim mold to make shiny rims for our cars. So die and mold meets us every day, also in private life, and we have to understand where these parts are coming from. There are many other examples. I don't want to show too much, but just want to give you an idea how complex these different parts are from different segments of this industry. Here we have a die-cast mold core. It's a cover where we have machined the form on our machine or one of our machines. Of course, when customers come to us, they always ask, can you do this on your machine? Can you support me to do this on this machine? And what is the cycle time? And can this machine make it faster? Depending on technology, of course, on for example, 5-axis machining is a big contribution to become faster on this, to become more industrialized, to be more productive. We show this to the customer that it's possible to make it faster, but at the end, the quality must be good, the part must be good. And this is in combination with the cost we have to achieve this. Also here are some examples of the details, how this part is finished with which kind of tools. So this gives you gave you hopefully a little introduction what DMG MORI is doing in the die and mold industry, how we are organized, who is DMG MORI, and what we are doing in die and mold industry. Now I want to come to another topic, talk about the trends and solutions. And we have identified, also working together with institutes, universities, we wanted to understand what is important in this industry today and what becomes important in the future. When we look back to the last century, where more this manual die and mold industry was more, everybody know what I mean, was more the philosophy of this industry. We have now seen a trend that it's more industrialized today. So today we see a lot of industrialized tool rooms which use modern technology, modern CAD/CAM systems, modern machine tools, 5-axis machining, and so on. And of course, when you look to the curve on the left-hand side, it's getting more flat now. This is the principle of this. When you have this change, and then of course you are in an area where, or in a time where you have to find a way how to differentiate. And here we have identified, not we as DMG MORI, but in discussion with others, what are, for example, 5 success factors for the future. And I've listed them here, and I will go in more detail during my talk, and we show examples. We have development of supplier network. There's nothing to do with the machine tool, but we think it's very important that our customers are doing this. Industrialization of the internal value chain. You will see what I mean when I come to this point. Mastery of efficient technologies chains. This goes very much detailed into the technology, where of course we have to look what we have done in the past, and we have to look in the future how we want to do these things in the future, and what opportunities we have in technology to become better and more productive and more efficient. Digitalization, a big buzzword in all industries. We come to this point. I will show a little bit more here how we do this here on our machine tools. And the 5th trend, mastery of additive manufacturing technologies. This then will be presented by my colleague Markus Bäumler. Important is that when companies in this industry are addressing these success factors, they increase or can increase the competitiveness in their business in long term. This is, I think, maybe there are even some more factors, but for us, this was the 5 most important ones. So let's go to the first one, supplier network. And we say that successful die and mold making companies maintain a supplier network and thus increase their own process impact force. So what does it mean? I'm from aerospace, and since last 15, 20 years, aerospace became a global industry, a global network, and especially from OEMs to the first years, they look to core competences and they try to get rid of the non-core competences and build up a supply chain worldwide. This had advantages, it has also disadvantages. We saw this during the pandemic, that this globalization, this suppliers all over the world is also a weakness. But I think a good middle way between both, a good compromise between make and buy, I think makes sense. And also what we see here in this die and mold industry, that this should be considered also in the future, that you should concentrate on what you're really good at, and where you're not good at, where you're not competitive enough, but you need this. You should have a network of suppliers who can support you. This can be, of course, for the work pieces itself, but it also could be along the process chain. And process chain means also from your planning to your engineering work, to the production, to the quality inspection, to your other jobs you have to do along this process chain. I think it's important to work together with the right partners, because together you get stronger here. On the second target, on the second trend, industrialization of the internal value chain, we have to understand that when we look to the tools, to the molds, around 35 to 45% cost which are produced making this is coming from machining. So machining is a very important part of this industry. And what we see today more and more is that our customers want to optimize. They want to work 24/7 in this industry. They're still working on single piece production sometimes, or most likely on single piece production. But today's technology offers us the opportunity to work 24/7. It's not mass production, we understand this, but it's possible. And here I think it's a big trend which should be followed in this industry more and more. And What does it mean finally? Productivity is key. You have to utilize your machine as much as possible because this is the investment which costs some money. And you have to use the right technology. I mentioned before 5-axis machining. The machines which are coming from this factory are all 5-axis. You don't need this for every component, for every mold, for every form, for every tool. But when you have it, you have a lot of opportunities to remove some other work. You can remove some EDM, for example, when you go into cavities by using 5-axis. With high-speed machines, with, for example, linear axis in the machine tool, you're becoming faster in the manufacturing, in the machining process, especially on the time when the spindle or the axes are moving without machining. You want to save the time. So productivity is key. The machine should be reliable and offer you a stable production process. Automation and lean manufacturing, of course, helps you to connect the machines or to reduce the manual intervention during the processes, so you can increase your productivity even for one-piece flow. It depends what kind of tools you're using along the process chain to prepare this work for the one piece. But if you do this in the right way, you also can optimize in this industry and become very productive, and you increase your value during your when you're looking to the internal value chain. Process safety is very important. In aerospace, we talk about green button processes. Means you have a complete automated process. We keep the door of the machine closed as long as possible, or at best, the best is to keep it closed during the whole process. This is also possible, of course, in this industry. Clamping, for example, is a very important point. It helps you to standardize your method of clamping when you do it in the right way. You have easy and fast setup situations where you can change the content of your pallet very fast, bring a new part on this to maximize utilization of your machine. And also with the right clamping, of course, you have a more safer process with less quality problems and a better final workpiece result. So also this topic, as an example, is important for this success factor 2 industrialization of the internal value chain. The third one I mentioned before, mastery of efficient technologies chains. What does this mean? Okay, man, at the end, technology drives the industry, drives the technology, drives finally our business success. And you have to look to this. You have to have people in your company who are looking for alternatives. Something you're doing since many years is probably good, but maybe there's something new. You should look at this and consider this. Here are some examples when you look to the CAD/CAM systems. When you have single piece production, of course, every part needs a specific NC program, but the parts are similar. You can work with standardized strategies, standardized tool parameters, and you can start to generate your CNC programs more automatically. It's not something you do from today to tomorrow, but this is the trend where our customers are working on today. When you look to your value chain, process chain, how you plan your parts, what kind of technologies you're using to achieve specific features on your part, look left and right. What is available today? What are the institutes, universities are doing today? What are your suppliers maybe on the machine tool, on your CAD/CAM system, on your tools are doing today? Bring them together, or also maybe join some events which we are organizing to see what is possible today. There's also one example about digitalization. When you 3D digitalization, when you have your part, when you have a 3D model of course you have your nominal model which comes from your CAD system, but if then you have also a model of your finished part, you can compare. You have much more information where you can learn and see how to improve your processes. So I think this are some ideas how to manage the production technologies in the company, and this is I think a very important discipline for the future to differentiate to your competition and to be global competitive. Coming to use of Digital Industry 4.0, here I will show you a little bit more what we are doing in DMG MORI when it comes to a process. And digitalization, of course, we have this. I started my career in the aerospace industry 30 years ago, and we did already digitalization with the tools we had at this time. Today, of course, the technology offers us a lot of opportunities. Everything is faster. We can work with more data, and it's really smart today. And I show you a little bit how we do this. DMG MORI itself, we have seen this since many years now, that this will become a big trend. So we offer solutions along the whole process chain, from planning solutions, preparation of your production, the production itself, monitoring service. We have digital solutions everywhere, and it would take I think 2 days to present all the solutions in detail to you. I only want to go in one area, which is very production specific, very machine and very process specific. These are so-called technology cycles, which is software which works on the machine tool to make the complexity of the machining process easier for you. You can easier handle the machine, you can easier program the machine, you can easier understand the results of the process of the machine, of the output of the machine, and this is a topic which I show now. I go a step back and because I want to show you how this can be used to understand and to monitor influences during the process, external influences on the process which affect your quality of the machining, which affect the accuracy of the machine tool, of the result of what you want to do. And that's why I go a step back. We see here a machine tool. Engineers who are developing these machine tools have a lot of experience to make sure that this machine tool is accurate. When our customers doing life cycle management over the time, when they use the machine, we make sure the machine is accurate over the whole life cycle. Finally, the machine has to have the ability to react on changes. Means when I do roughing or finishing, you can imagine there are different temperatures in the spindle or in the machine due to the forces and due to some cooling measures in the machine and the thermal stability. The machine knows how to react to be accurate in both scenarios. However, we have some environmental influences. We're never in a perfect production hall. Maybe they're air conditioned, but we have sometimes some wind, cold wind, warm wind goes through the factory. We have some windows where sunshine comes through and heats up the machine tool. We have even temperature changes in the factory, either morning or in the afternoon, or summer and winter. And we know from the physics that steel, for example, will expand when it gets warmer. And we have to find solutions with this. We have the machining quality, which is important for us. But we have, of course, the machine tool, which has some influences or which is affected by influences. We have these environmental influences. And we have the process itself, the machining, the cutting process. And altogether make finally the quality which we need on our workpiece, on our mold, on our form, whatever we machine at this time. The cutting process is very dependent on the tool wear, because when we cut, the tool gets worn, and after some time we have to change it. This is also dependent on the material we are cutting, on the cutting parameters, whether we do roughing or finishing, or whether we do goods machining, or we have maybe poor parameters, has influence on the tool wear. Lubricant coolant, underestimated in many cases, but the quality of the coolant, the concentration, and so on, they have big impact on the cutting process, on the quality of the component finally, because it affects the tool wear. We have others like clamping. When we have a very poor clamping and we have vibrations during cutting, we see this on our workpiece later. So we have an influence on the tool wear again. And I show you how we take care of this tool wear, how we can monitor this, and this is where we are today, but there's a lot in the future which we expect also to be developed and give us more opportunities to react on these influences. We know it's coming, but we don't know when it's coming, or we don't know exactly when it's coming. What is your target in your factory? It's cost. You are earning money with work you're doing for your customers, with the work pieces you deliver to the customers. So you're influenced by the machine tool, by the factory, by the environment. Of course, people also cost money, and the tools cost money, and there's much more, of course. And when you don't have your process under control, you have to do a lot of additional measurements during or after machining to achieve the required workpiece quality, either by interacting the process or making rework afterwards. And this is all additional cost, which sometimes you really don't see. It's there, and you have to pay for this, but you should avoid this. And here again, we have to take care of these external influences and make sure that the machine tool can react in the right way. So we're looking a little bit to this toolware issue, because I think it's very important, and it's a part of our investigations we are doing at the moment deeply with digitalization. For this, we have so-called sensor-based technology cycles. So what is this again? Sensor technology cycle is a software, and sensor-based means there are specific sensors in the machine tool which can communicate with the software. They deliver information, and the software can decide, that's good information, I can continue, or it's not good information, I have to do something. And this is what we call sensor-based technology cycles. Sometimes I compare this with innovative assistance systems. Today, we are used to this every day when we go to work in our car. We have a lane assistance, we have a braking assistance, we have a lot of assistance systems in our cars. They help us to make driving easier and more safer. And this is what also these systems are doing. I will show you 3 of them, and just for you to understand how important this is and how important this becomes for the future, and which opportunities we will get in the future by using this kind of technology. First of all, when we have sensors, we produce data, and we want to see the data. As a human being, as an engineer, as an operator, we want to see what really happens in the machine. From experience, we know if there's a noise, if there's a vibration, there's a chatter on the workpiece maybe. There's maybe a higher tool because of this noise. But when we have the data, we have something very neutral. It's not louder, not less louder. It's data. It's black and white for us, and that's why we are trying to visualize the data on a very easy way. It can be visualized on the machine tool, on the control screen. It can be done in the office in a connected computer, but you can see the data and can learn from this. And this is very important to start with digitalization in the process. So I show you a little bit of practical examples how this can work. Here we have a solution which we call MPC. There are sensors which are measuring the torque in the spindle. They're measuring the shock which hits the spindle, and they measure the vibration which can come from the tool, of course, if there's an unbalance, for example. And there's a second one which is more sensitive. We call this CCC. It measures the pull-in force, so which force is required, or which is at the moment used to clamp the tool. It measures the bending moments. This becomes important in the next slides. It measures also forces during cutting and the tool symmetry. So we get already a lot of information of the tool, which is affecting the workpiece and is producing finally the quality. And then last but not least, there's one we call fluid analyzer. It measures constantly the temperature, the pH value, and the concentration of the cutting fluid, which I said before. Concentration is important for the cutting process, for the toolware. If we are out of a specific limit, we get a bad quality, and we want to avoid this. We want to monitor this. We have to monitor this. When we use this kind of tools, and these are just some examples, we can increase our quality, our performance, and our availability, which means in other words, the OEE of the machine can be increased. Finally, we can make more money with cutting. So I said I show you some practical examples, and here's an example where we clamp a part into a vise, and we do it wrongly. We have an overhang which should not be there, but this is a mistake which can happen in the workshop. And the cutter approached the part, and here the sensor says stop, because the shock on the spindle was too high. It stops immediately, and we can see here on this little movie, the tool is still okay, because the sensor was able to react so fast that the tool is okay, the spindle is okay, the machine is okay. There's no repair required. It was a mistake, but there was no effect. There was no problem. We can look to the data. We see, okay, there was a shock. We see the signal. We understand what is the root cause. We correct the clamping and start again. And then we have now the right process. And we also can see it continues. The cutting continues without any damage to the machine tool, to the workpiece, to the tool. So sensors really are very helpful to avoid big problems when we do little mistakes sometimes. There's another example which is coming from our own shop floor, where we make here a spindle casing from a casting. Also here a big tool. There's an unbalance, and the machine stops due to the unbalance in the tool. We go to the analysis immediately on the machine to look to the data, learn what happened here. what was this noise? We understand the noise was a vibration. We look to the tool. There's a cutting edge broken. This is the root cause for the unbalance. We use this information. We reprogram, and then we make the next part. Same problem happens. The tool edge breaks. System can recognize it. Here we also automatically exchange to a sister tool, and we continue machining. And this is a video which was taken here in our own production, and we do this. We produce here 3 shifts in this shop, in this machine shop, and in the next morning they have good parts. They have no damaged parts. They have good parts, high quality, because the machine was able to react on these unplanned events automatically. Yeah, we have the other one which is more sensitive, where we measure. We have 20 sensors in the spindle, where we can measure very sensitive information, pull-in force, bending moment, forces in tool symmetry. For example, when you have your tool in the tool holder, and if there's a chip maybe between tool holder and the nose of the spindle, where both come together, you have a problem later, because your plane surface is not really plane. You have a displacement of your tool, and depending on the length of your tool, you have a displacement of your cutter and of the tool center point, and then you have a mistake or you have a failure on your component. When you have no sensor, you will not see it. You will see it later when you have your part finished. You see there's a problem. The sensor can detect this and can measure this and can say, no, I don't start. It will show you on the machine tool on the picture where the chip or the damage was detected. The operator can remove it, or you can do that automatically with a cone cleaning in the tool magazine. You can do an iteration process. You can program this, and then you avoid the machine stop. You avoid this issue, this problem on your workpiece, by just using a simple sensor signal to detect this system. And customers tell us they don't have this every day, but once a year you have this problem, and you can avoid scrap on your component or quality problem. These solutions are really useful for this. I said before, the bending moment is a also interesting signal which we can receive from the system. Just put here in a simple picture what the bending moment means. When you cut the metal with a milling tool, you go in the cutting direction, and there's a force against the cutting direction, and you can measure the force. You can measure also forces on the axis. You can measure the load of the spindle. But when you then look to the set, which is the length of the tool, and you multiply the force and the set, the length of the tool, you get the bending moment. And this multiplying this, you all know from physics, this gives you a very high number. And this means you get a very sensitive signal to see how much force the tool has to work against when it machines. And we have seen that when the tool gets more worn, the force is getting higher, because there's more force required to machine the part. And we use this. And this example here in this movie shows how we machine a pocket with a tool, and the system recognizes the bending moment is too high. It stops, change the tool automatically, and then continues the cut with a new tool with a bending moment which is normal, because we know the normal bending moment, or the value which we see here represents a new tool, or a tool which is not worn to the limit which we have defined before. Also here we look into the data, we understand the reality and compare this data. We make use of this. We also can look to other data, whether we find something which we think is maybe, we have to question ourselves again, what happens here in the process. But the data show us the reality, and we can take corrective actions in our process and make our processes more reliable, more safer, that we can have more autonomous machining and can use the full range of automation to have 24/7 production. Many customers are asking us, what is now the reality between the data? We don't understand this, and for this we did some tests here also. What you see here is one cutting edge of a 4-flute cutter. It's a solid carbide cutter, diameter 6 millimeter, which we use very often for machining. And we see over the time, more than 70 minutes, that tool wear is going up step by step. We also measured this tool wear We measured all the other cutting edges as well over this time, and we can see something we have really expected before we did this test. The tool wear is increasing at the beginning linear, and later it increased exponential, which is a typical sign that now the tool is going to its end. So the tool wear is starting to really bring in some big damages in the tool, and then there should be a very good time to stop now and to use a new tool, because it's not very likely that we don't do good quality with this tool anymore. Then we look to the bending moment, and we can see the same profile of the data as well. So the left-hand side, real tool wear, right-hand side, the signal. And we see the same profile at the beginning linear, and later it goes up exponential. And this gives us a lot of confidence that working with data, with sensor data, and when we understand the reality and the data, and we can combine this, that we can use then digitalization really, really well to make sure that we can better understand the processes, we can optimize the processes based on the data, of course, mixed with our experiences, but we have in addition the data, and then we can secure the processes. So what is our vision here? What is next here? And on the left-hand side, you see onboard assistance systems. This is where we are today. We have the machine tool, we have an operator, we have already these systems, these technology cycles with sensors, which helps us to understand the process, which stops us, which is our braking system, our braking assistant, our lane assistance. We have this already, but we want to go to the right side, to the right-hand side, to the vision. We want to have autonomous machining. We don't want to stop the machine all the time. We don't want to have manual intervention. Maybe we have to have some adaptations during the process automatically. Maybe we even don't want to inspect the part anymore because we rely on the data. We have maybe digital workpieces, digital twins in the future, which really represent the real part, and from the data we can read how good the part is. From the left to right, there's something to do, of course. This year we will have a solution for analytics, data analytics, where we give our customers a tool where they can visualize the process and the data in a very smart way. It's like a video recorder. You can look again to the process and understand what happened here. And you can also set some rules and secure your process later. Future, of course, there will be advanced analytics to understand the correlation between the processes which are in the process chain. We will see self-learning artificial intelligence, which we need to make better predictions based on the data. But this is really, when we think about Industry 4.0, how to use this in machining processes, this is a nice thing where we think we definitely will develop more in this area to give our customers a possibility to follow this vision in the future, to come to more autonomous machining in all industries, not just mass production, also single piece flow, specifically in the die mold industry. Yeah, this was my fourth trend, which I wanted to show in more detail. And this is also end of my part of my presentation. And now I would like to hand over to Markus Bäumler, who will give us his point of view for additive manufacturing and what advantages he sees in the die mold industry. So I click to my next slide, and I think we have the other presentation now. Thank you.
Thank you, Michael. You need to support me with the next presentation. Okay, thank you. So my name is Markus Bäumler. I'm in charge of sales for the laser machines within DMG MORI. And today, actually, I would like to take you to a journey of where additive manufacturing can get used for the die and mold industry. My focus will be actually the die-cast mold industry, or die-cast molds in general. The presentation title is Cost and Lead Time Reduction in the Repair and Manufacturing of Die-Cast Molds. Before I would like to take a deep dive, I would like to show you what kind of technologies we can offer. So on the left-hand side, you do see the powder bed system. So actually, this is probably by far more known in the industry, to the industry. And on the right-hand side, you can see the powder nozzle principle, the so-called DED, directed energy deposition, the full name is. So if we compare these two processes, on the left-hand side, you have a machine bed filled up with powder. In our portfolio, we can offer a space of 300 by 300 by 300 millimeter. That machine bed is filled up with metal powder, and that machine is able to print very detailed cavities, very detailed parts, thin wall structures in different materials. Also titanium, for example, and aluminum is possible, besides, of course, of the tool steel. The technology I would like to set the highlight today is on the right-hand side, is the powder nozzle principle, is directed energy deposition. So here we are spraying powder through a nozzle. Here on the picture, you can see a cross section through that nozzle. The material, the metal material, is being transported by argon as a transport gas. We spray that powder through a nozzle, we hit it with a laser beam and melt it up layer per layer. And with this technology, we can achieve really nice things for the die and mold industry. The beauty of that system is that it is a hybrid system. So it is two processes in one machine. And the formula on top, you can see 1 + 1 is more than 2. Actually, this is not a failure in our mathematics skills. Actually, what we would like to impress is, or express, is the ability of the machine to optimize your existing process due to the fact that you don't have material handling times, due to the fact that you don't need to set up a machine twice. That machine is combining, or that process of hybrid additive manufacturing is combining laser deposition welding and milling in one machine. And this is a big chance for the industry to save, to optimize your existing processes. And by doing this, we can achieve many great stories, success stories for the die and mold industry, which we can see on that slide here. So from die cast molds to plastic injection molds, hot forming tools, cold forming tools, cutting knives, and forging tools. The beauty of that is that we are always talking about more or less an already existing tool. So that tool which got conventionally manufactured on the ways you are doing it today, but we give that molds, we give these molds or tools a second life. And this is what can be done and optimized with our technology. For example, for die cast molds, the best example is, we just have heard from Michael's presentation, 35% of the total cost for the die and mold industry is coming through machining. So you would like to give that mold a second life. And this is what we can offer to the industry by using that kind of system or that kind of solution. So we can repair existing tools. The next one is, for example, in use for the plastic injection molds. You can see that copper alloy on the mold. And the benefit here is that we can play, that we can use multi-material. So we are not limited to steel, tool steel. We also can use different materials which could bring an optimization to the process. For example, to pull out heat. The next one, for hot forming tools, also a very nice example. Hot forming tools are facing highly abrasive process, and to repair these, so far they either get repaired manually or with old-fashioned ways of manual welding. That system can do it all in one combined setup by adding a highly wear-resistant material with a very high hardness, for example, and with a very high wear resistance. For cold forming tools, I brought an example here. The beauty here is that we can homogenize the tools, for example. Imagine you have tools in use and need to have a big stock of different tools. So actually, the beauty of the system here is that you use one common base and print on demand to whatever version of that tool you need to have. So you can reduce your stocks. You also can reduce, for example, the lead time due to the fact that you are always able to deliver. And how important delivery is, we are facing issues at the moment through the whole industry. Lead time is critical, and with this kind of process, I think we can do a big optimization. Next one, cutting knives. Again, a beautiful example of what the ability is to combine two different materials due to the fact that we are combining a very resistant material in the base and the hard material on top. The material we are cladding, the material we are adding on top on the base is offering a hardness of HRC 63. So you can totally skip, for example, the hardening process afterwards. Forging tools, here in brackets, simple. This is something we would like to have a closer look in future. At the moment, we are developing the process for that. For all of these applications, which are relating to the die and mold industry, we already have industrial users. So please contact us if you should have more information required on that. I would like to highlight today the capability of two processes. One is, like we can see on the left-hand side, the repair. We have just heard repairing of very expensive die-cast molds is very important due to the fact that lots of costs are related to produce these kinds of tools. So you would like to give it a second life, and this is what we can do here on the left-hand side. On the right-hand side, you can see the benefits of the process due to the fact that additive manufacturing is able to print a mold, for example, do it in multi-material and add a cooling channel to the inside. Let's have a look at repair at first. The picture marked with 1 is the status of the worn out die before it gets repaired. On the picture number 2, you then define what segments do require repair. We mill away these segments, start the additive process, picture number 4, and then mill the part, the component in the same machine, in the same clamping down to net shape. The benefit here is that compared to the manual process, we can increase the lifetime by factor 3. So this is giving a great opportunity to the industry to save cost. Yeah. Different example, different customer, more or less the same story. You have a highly expensive die-cast mold, and this die-cast mold is worn out and requires repair. And we have highlighted 2 different segments, one marked with yellow, where coating, for example, is good enough, and one marked with orange, where coating is not good enough due to the fact that the base material already is damaged, already is having cracks and so on. What we are doing here is we can design or decide in the NC programming path which way we would like to go. If coating is enough, we just add a little bit of material. Or if you decide the way of completely taking out the orange marked sections and build them from scratch on the existent tool. And this is what we have done on the orange mark area. Compared to the existing process, the cost saving or the saving in production throughput time was approximately 70%. So this was a very convincing factor here to go forward with this technology. Another beautiful example of repair we can see here, company Friedrich Deutsch, the red marked rib more or less is damaged, requires repair. We have there decided to take it out, to mill it out, to build it completely from scratch. This is what we can see here, bottom left, and mill it down to net shape, bottom right. Compared to the existing process, we have a significant reduction in throughput time. And of course, this is bringing the customer a big effect in terms of how many tool sets he requires. So usually our customers are using 2, sometimes even 3 sets of tool sets. Here, due to the fact that the repair is not taking very long, the customer has the opportunity to reduce 1 set of tools. This was what we can do, what we can offer for repair. This is what additive manufacturing in general can do for repair. Now let's have a look what is able, if you are drifting away from existing tool designs to a new approach to new opportunities which the industry is giving for the die and mold parts. And this is what we call the new multi-material die cast molds with cooling channels. And of course, this presentation is related to die cast molds. Please also find the analogy for your process if you should be in a different in a different industry for the die and mold parts. For example, for plastic injection molding and so on. Here, our customer had a big problem. The problem was that this engine bracket, which got produced actually from the die cast tool set our customer has done, had a significant problem in quality. And the scrap rate the customer has produced was too high to be cost efficient. And by designing, in combination with voestalpine and the DGH group, a new kind of die cast mold, we have achieved a significant reduction in production cost, a significant reduction of the scrap rate. All in all, 600,000 engine brackets, which are in use for the Volkswagen engine, got produced with a significant reduction of scrap rate. How the mold looks like, you can see here, top left and top right, you can see how it looks from the inside. And this approach, this benefit the DED technology can bring to the industry. So here we see the nice intersection between the copper alloy core and the outer skin, which was made from tool steel, in combination to the internal cooling supply. Looking at the key facts of what has been achieved, please check out what we can offer or what the technology can offer. The scrap rate, it doesn't sound much, got reduced by 3.4%, but 3.4% scrap rate reduction at a production volume of 600,000 parts is a total saving for just one component per year of 180,000 parts. So, of course, additive manufacturing is a quite cost-intense production method. But by using this kind of technology, the benefits overcompensate the higher cost for the mold. The higher cost of the mold is 832 euro per mold. But the total investment, due to the fact that 15 molds were in use to produce 600,000 finished parts, total investment only was 12,480 euro. And the saving was 180,000 euro. So there is a very quick ROE that technology can bring to the industry. Here we have a comparison, what the cost is for a conventional mold and what the costs are for the DED built mold. So this is where this 832 euro is coming from, to give you some background information on that. Additive manufacturing always is more expensive for that one single part. But additive manufacturing is solving issues, quality issues, in this case, to make that part, you can see here, die-cast able. Yeah? Before it wasn't, now it is. So by putting this multi-material approach, by putting these internal cooling channels, the heat got reduced in the die-cast process significantly. In this example, approximately 40% less heat. I think 3 seconds after the shot, yeah, exactly here. 3 seconds after the shot, the heat, this is the mold, yeah. On that point, the heat got reduced by 90 degrees, which is 40%. And by reducing the heat, of course, you have optimized the quality due to the fact during the solidification of the aluminum, you are generating less pores or move the pores in areas of no concern. But also due to the fact that the thermoconductivity of the mold is higher, you are also able to increase the output. So please remember and make use of this kind of information. Multi-material in line with internal cooling supply is a big, big opportunity. Additive manufacturing, sometimes people are a little bit shocked of, oh, this is a new technology. I don't see any approach for my company. I don't see any opportunity for my company. Maybe at the moment, not yet for manufacturing of new parts, but I'm sure it offers the right solution for repairing. So please still have in your head, repair on one side of existing tools and the other one generating of new, highly complex parts, yeah, to optimize a not yet existent manufacturing problem. Additive manufacturing, as mentioned, we from DMG MORI offer selective laser melting, LaserTech SLM called, and on the other side, LaserTech DED, are widely in the industry. This matrix we show here is quite easy to read. So on the x-axis, you can see the technology maturity index, how mature, how technical available in terms of problems is that kind of technology. On the y-axis, you see the industrialization. So how many systems are there already in use? For both technologies DMG MORI offers, we can say these technologies are highly mature and of course also available on the market. Yeah, I admit the SLM technology, in our example, the LaserTech 30 SLM, for example, there is much more installations due to the fact that this is already existent for approximately 3 decades. The DED technology we can offer is highly mature as well. The number of installations so far is not yet as high, but it is in the industry and it is available. And we have impressive references. What our unique setup is, it's a combination between an existing milling machine and an additive manufacturing solution. All in all, there is nevertheless more than 70 installations of the DED technology. And by looking to that installations, we can say that approximately 40 to 50% of these installations are in die and mold. If this should be of interest to you, please contact us at any time. And I think now there's the time to answer some questions for you.
Thank you, Markus, for this deep insight in additive manufacturing. And we hope that this agenda, these topics are very interesting for you and added some value to your thinking about technology and about what is next, what will come in the future, what it becomes important for yourself and for your companies, and so we really wanted to give you some information, background information, how we at DMG MORI think about this industry and what we think is important for the future. And we're happy to have discussions on this, and looking forward to your questions.
Okay, so we have already a few questions from our audience, and I will start with Kamal Jain regarding the film that you show during your presentation, Michael. Asking is the very fine machining of molds. Is this hardened steel that is being machined on your movie?
I probably didn't get the question right, but yeah, it is this whole form was machined on this 5-axis machine.
Yes, yes.
And,
from the movie, what is the material that you were machining at the
material?
The material.
I don't have in mind. I think it was on the slide. I don't know whether my colleagues can go back to the slide. Can you go back to the slide? Maybe manually.
I think the point is, was it hard machining?
Yes, it's this hardened steel that is being machined. So they need to know the material. They are asking about the material.
It's a here we see it 40 chrome mangan molybdenum 1.2312. This was the material which we have used, which is, as far as I understand, standard steel in this industry.
Yeah. Another question is the application on diamol different in compared to the application to the areas or products as aerospace in the case of additive manufacturing?
I mean, there are many differences, but also many things which are very similar. Materials are different, the geometry of parts are different. Sometimes the value is different depending on the material, of course. But what I see, which is very common between both industries, is the need of this industrialization, the need of these automatic processes, where we have to, when we look to the process itself, we have to make the process as reliable as possible. Whether it's an aerospace part or it's a die form or whatever we machine for many hours, we have to enable the process or the machine that it can run very autonomous for a long time. That's why we need measurement through it during the process. We need maybe in the future more of these sensors to monitor and control the process. I think this is something in common, which is, but this is in common for all industries, what we see as a trend, where in the past companies, independent bridge industry, they machined something, opened the door of the machine tool, make some corrective actions on the machine, measured something, make some corrections on the control. And this is yesterday. This is gone in the future. So machine door should be closed for all the time. It's a CNC controlled machine which can run autonomously for many hours, but we have to keep the process under control. And this is, I think, which is common in all industries today. And here we have, of course, appropriate CAD/CAM systems which can support us to build up the process. And the machine tools today are very capable to support also this trend.
Also from Andrea van der Muur, I hope I did it correctly, I said correctly. Please comment on the surface finish of the additive deposition area.
So right after building an additive surface, now speaking about the DED process, you can expect a RA surface finish of something like RA16. Okay, I admit this is shocking for the typical standard, but of course you are not using that surface finish for the actual process afterwards. We are always finishing in the same machine, in the same clamping. So by DED, you are able to do approximately RA16. And now speaking about SLM, the surface finish, due to the fact that the layers are much thinner, is much better. So here in that range, you are looking at something like RA 3 point something. Yeah. So in that range. Yeah. Mm-hmm. The strength of the DED process and the DED hybrid process is that you can do right after milling, right after building, the milling operation to get to a surface finish RA 0.2, something like that, is possible without any problem. Yeah?
Yeah. I have another issue. I think is also related with additive manufacturing, that is coming from a routing. Besides buying the machine, are people offering this as a service?
Yes, there is more and more people. So we have seen that installation of 70 machines to the market. There's also some companies offering the machine capability as a job shopper. Please contact us if you should require a contact partner. We are happy to share them.
Another question from Andre. Are you machining the hardness material, hardness of 60?
Yes, so we actually can print that kind of material. We have seen it on the cutting knife. If you remember, the base material had a hardness of HRC 44. The material we are using there is called Ferro 44. And that material we are topping with the material called M2, yeah, and this is an air quenched material. It is offering a hardness right after building of HRC 62 to 65, somewhere in that range.
Okay, thank you. So I have no further questions from our audience. So, Bob, you want to make any question or comment?
Yeah, I have a couple of comments. I mean, firstly, to Michael and Marcus, I'm sure this is the first time you presented a world-class presentation to 19 countries simultaneously. And it indicates the power of ISMA, and I'm really pleased that you've taken up this opportunity. Manuel, I think the guys have actually set a rather high bar for the rest of the global partners. This is going to be an interesting year.
Right.
Maybe we'll start a little bit of a competition between them.
Yeah, welcome.
It was a very good introduction, and the presentation and the case studies that you introduced were very nice, and I think make it very clear what is happening in these areas. So perfect.
Yeah, thank you to ISMA to having us for this hopefully long row of further webinars, but of course we were the first ones, so thank you for giving us the opportunity. It was a big pleasure for us, a big honor to be the first one. And yeah, I'm looking also forward to the next ones, and I think it's a very good idea to have this organized now, that we all can learn from each other and exchange our ideas and discuss this, and also looking forward to meet everybody again in person, which makes it, I think, even more effective. But yeah, we are very happy that we were part of this. Thank you very much.
Great. Thank you. Thank you, Marcus and Michael. So Bob, up to you to end up this session and to announce what will be the next topic for the future, our future webinars.
Yes, well, thank you very much, Manuel. The next topic is, or the next global partner to be presenting will be Makino. Now they're going to be doing something quite interesting, because they're going to be talking about industrial developments in consequence of COVID-19. We don't know much more than that at this stage, but I think this is going to be an interesting twist and something to look forward to. So what more can I say? Thank you to everybody globally. it's still good morning to some of you, it's still good day to some of you, and it's a very late evening for the rest of you. I myself am now going to jump into my car and go and join some DMG MORI customers at our local center for a glass of wine. So thank you very much, and great having you on board. Thank you. Bye-bye.
Thank
Thank
you.
you. Bye-bye.
Goodbye.
Bye.